welcome to the course on biostatistics and design of experiments. We will talk about chi-square distribution, then chi-square test. This is very important, especially when you are looking at data where we are talking about some sort of a binomial data, yes, no, live, dead, 1, 0 and that sort of situation. Okay. Now, what is chi-square distribution? This is also a continuous distribution, okay, just like your normal, but then it is somewhat related to binomial at some point. We will come to that actually. It is asymmetric and depends on the degrees of freedom. For example, if you have very low degree of freedom, it looks like this. As the degree of freedom increases, you end up slowly having, okay, skewed and so on actually. Okay. So, it is used to construct confidence interval for variance. Generally, chi-square is used for variance ratios. Okay. It can be used to compare a set of actual frequencies with the expected. Okay. So, I expect a certain number of child mortality in a village, but the current data is this much. Is it significant or not significant? I expect to have a certain number of defects when I manufacture bolts, but I see so many defects in a day. But so, is it significantly different or not? Such sort of situations actually. So, it is actual frequencies versus the expected frequencies. Okay. So, it is like we are trying to fit with the theoretical distribution, okay, and then check for the goodness of the fit actually. So, I expect a particular sort of values, but I find this, like I expect 60 to 70% marks of 10 students in a class and 70 to 80 of another 10 students in a class and above 90% another 10 students, but I find different numbers in that range of 60 to 70, 70 to 80, 90. Now, is that really a significant difference? It also looks at association between variables in a table. We will talk about this contingency table later on actually. So, I make some equipments, some parts using 3 or 4 different equipments, and I find defects in each of the equipment. So, defect, non-defect, defect, non-defect, equipment 1, equipment 2, equipment 3. Is there a relationship between the defects and the equipment? So, I can use a chi-square test for that. This is very useful, especially in clinical trials. We may be running a lot of samples on HPLCs, and some HPLCs may give very accurate result. So, it is acceptable. Some HPLCs sometimes they give accurate, sometimes they give non-accurate, which is not acceptable. So, I may have 100 samples injected in HPLC 1, I may have say 30 rejected and 70 accepted. I may have 110 samples injected in HPLC 2, I may have 40 rejected and 70 accepted, and so on actually. So, is there an association between the rejects and the instrument? For that sort of situation, I can use something called the chi-square distribution. Okay. So, for example, a company wishes to know if the events of defects is related to work shift. This is very common in industries, you know, like in industries people come in the morning shift like 8 a.m. To say 4 p.m. and then there will be second shift which could be 4 p.m. to midnight 12 o'clock, and then there could be a third shift which could be midnight 12 o'clock right up to 8 a.m. Now, each of these workers in each of these shifts are manufacturing a particular part like bolts for example. Now, you find some failures in some shifts, some successes in some shifts, morning shift, after evening shift and night shift. Now, is there an association? You want to know, because it is always considered that people working in the night shifts may always make mistakes. So, mostly defects come in the night shifts. So, is there an association between the defects or the failures as against the shift, that is the time in which workers work? So, this type of situation also we use this chi-square distribution and chi-square test. So, in each of these it is very powerful for you to look at chi-square type of distribution. And of course, as I said, in biological situation it is very useful because you are telling we expect a mortality of say 10%, and then we find in a few villages different numbers. Is it significantly different? Okay. In that sort of situation we can use this type of chi-square test. Actually, you are testing a drug, it shows successes, it shows failures. Okay. You are testing a placebo, it shows successes, it shows failures. Now, is there a difference between the placebo and the drug, or there is no difference? We use the chi-square test actually. Okay. So, it is a continuous distribution, and it gets skewed like this. At very low DF it looks like this, and as the DF keeps increasing it is slowly becoming more uniform, and at very large DF you may end up having some sort of a nice smooth uniformly distributed picture. Okay. So, the equation for this looks like this, y not, okay, chi-square value, this is the probability density function, this is nothing but the degrees of freedom. Okay. So, this is how this equation looks like. So, y is equal to y naught is a constant, okay, constant that depends on the number of degrees of freedom. Chi-square is the probability density function, and okay, that is how you calculate it. Okay. So, it is generally it is positively skewed, like I showed you, positively skewed, okay, generally, but as the degrees of freedom keeps increasing the distribution can be approximated to normal. Look at this, this is 40 degrees of freedom, it looks almost like a normal distribution. Okay. So, what are the 20 degrees, you can still see the skewness here. Okay. That is why it is generally believed that if you have 30 or more degrees of freedom it will approximate to a normal distribution. So, the mean of a chi-square distribution is the degree of freedom, that is mu is equal to this value V or nu it is called actually, that is the DF. Variance is equal to 2 times the number of degrees of freedom. So, sigma square is equal to 2 DF. So, in a chi-square distribution, okay, so the mean is equal to the number of degrees of freedom and the variance will be 2 times that. When DF is greater than or equal to 2, the maximum value for y takes place when chi-square is equal to okay, nu degrees of freedom minus 2. Do you understand? As the degree of freedom increases, that means the maximum value, okay, occurs for the y when chi-square is equal to, okay, DF minus 2. Imagine I have degrees of freedom as 3, so maximum value will occur at 3 minus 2 1. Okay. Okay. As the degree of freedom increases, the chi-square curve approaches normal distribution, as you can see from here. Okay. So, the chi-square will have a mean of degrees of freedom, the variance will be 2 times the degrees of freedom. So, we can get the cumulative probability also. The total area under the curve is equal to 1, generally it is put into that, and the area under the curve between 0 and chi-square value is this cumulative, this is the area. Okay. So, the distribution generally looks like this with a long tail, because as I said it has got a positive skewness. So, this is how it looks like. Okay. Here it rises very fast and then it falls down and then it keeps on going. So, if you are talking about cumulative for chi-square is equal to 5, then this is the entire area. Okay. This is the entire area, but the total area under this curve is equal to 1. Okay. So, it gives the probability that the value of chi-square statistics will fall between 0 and 5. So, just like your T distribution, normal distribution. So, if chi-square is equal to 5, okay, the probability, the area under the curve is the probability, because this whole area is 1, the whole probability is 1. So, this gives you the probability that your chi-square will lie between 0 and 5. Do you understand? Okay. So, chi square lying between 0 and 5 is given by this shaded area. If you take the whole area, the probability is 1 and the area is also 1. Okay. So, just like T table, Z table, F table, we also have a table for chi square, and you have here the degrees of freedom, okay, and then here we have the alpha, and of course you see, as you can see, two sided and one sided. So, one sided will be half of this, 0.05 means 0.025, 0.01 two sided means 0.005, obvious, right. So, this is how it looks like. Okay. So, for different degrees of freedom, you will have two columns here. Okay. This A is the lower boundary, that is on the left hand side critical value, B is the upper boundary right hand side, okay, on the right hand side, and that one is upper bound. So, you see there is a lot of difference in the magnitude. Why is that? That is because the way the shape of the curve looks like. Okay. So, if I put in here a line here, for example, and a line here for the area, because it is rising very sharply, you will have very small value, and because it is falling down very slowly, you will have very large value. That is why if you look here, the A and B, you can see small number, and on the B is a very large number, small number, very large number. So, like that it goes actually. Do you understand? Okay. And this top one relates to two sided, bottom one relates to one sided. So, we use it for two tailed test and one sided test as obvious, right. So, we prepare the test statistics, and then we compare from both the table for the upper boundaries and the table for the lower boundaries as well. The test statistics which we use, I will tell you what the test statistic is greater than the upper tail, okay, value or less than the lower tail critical value, we reject the null hypothesis. So, if I am looking at this, and if my test statistics for chi square comes out to be say for example larger than 2.71, then I reject the null hypothesis, okay, for 1 degree of freedom, for a probability of two sided 0.2, I am saying 2.71. So, for 1 degree of freedom, probability two sided 0.05, if I get more than 5.02, if my chi square calculated is more than 5.02, then I reject the null hypothesis. You understand? Same thing here, 3.84 for a one sided test. If I get more than 3.84 when I calculate the chi square, I reject the null hypothesis. This is how you do, and this as you go down, we are having more degrees of freedom coming into the picture. Okay. So, this chi square test can be used for contingency tables, it can be used for comparing two different distributions, it can be used for comparing expected versus observed, and so on. We will look at each one of them slightly more in detail. So, you can use chi square for a population variance. So, I have a sample variance, I want to know whether it comes from that population. So, I have a sample n values x1, x2, x3 up to xn. So, I can calculate mean and variance, okay, S square for this one. Now, I want to know whether this S square comes from the population of sigma naught. So, obviously, what is the test statistics here? N minus 1 S square divided by sigma naught square, n is the number of data points. So, this is the test statistic, okay. And then we based on the number of degrees of freedom, based on our level of test, you take the appropriate table chi square value and see whether this value is greater than the table value. In that case, we can reject the null hypothesis, saying that null hypothesis they come from the same population, alternate is they do not come from the same population, and we can use either one tail or two tail test actually. So, the null hypothesis will always be status quo, they come from the same population, that means the sample comes from the same population. Alternate will be the sample does not come from the same population, okay. So, let us look at this simple problem, just understanding. So, the null hypothesis they come sigma square is equal to sigma naught square, okay. Alternate is they are not. What is the test statistics? Like I said, n minus 1. So, I have a sample, right. So, n minus 1 s square, s is your standard deviation, okay, divided by sigma naught square. So, sigma is given by 4, okay. Number of data points is 17, s square is 7, okay. So, 16, so this will be 16 multiplied by 4, okay, 16 into 4 divided by okay, sorry, 16 into 7 divided by 4, 16 because the number of data points is 17, okay, 16, okay, into 7 divided by 4, 4 is your sigma. So, 16 by 4 is 4, 4 into 7 is 28. Okay. So, from the test statistics we get chi square is equal to 28. So, we have 17 data points. So, 16 degrees of freedom, okay, 16 degrees of freedom is in this row, and we are suppose we look at two-sided 95%, that is this place, okay, two-sided 95% is this place, okay, one-sided 95% will be this place, this column. So, two-sided 95, so we will go here, it is 28.85, okay. So, we calculate as 28.0, see we accept the null hypothesis, okay, for a one-sided test, for a one-sided test or a two-sided test. Okay. Suppose we take 28 point. Suppose we take the other one, that is why we take a one-sided test, okay, instead of a two-sided 95%, then it will become 26.3, okay, here. So, we can reject the null hypothesis. So, if it is a two-sided 95%, it will become 28.85, the test statistics is 28. So, obviously we cannot reject the null hypothesis. If it is a one-sided 95%, then your table is 26.3, so your test statistics is 28. So, we reject the null hypothesis, okay, depending upon what is your hypothesis that is being developed. Okay, now we can use this for testing the goodness of fit also. So, what do? We look at the observed, we look at the expected, okay. Expected is your theoretical value. So, observed minus expected square divided by expected and sum it up. So, I have 10 data points means I do 10 summation, observed minus expected divided by expected, here you have a square term actually. Okay. So, your null hypothesis is equal to observed is equal to expected, alternate will be observed is not equal to expected. So, remember your test statistics is compared with then the null hypothesis is observed is equal to expected, alternate is observed is not equal to expected, and then after that what do? You go to your table, okay. If your test statistics is greater than the critical value, we reject the null hypothesis, okay, that the observed is equal to theoretical distribution, okay. Otherwise we accept the null hypothesis, okay. Okay, let us again look at a simple problem. We are comparing observed frequencies against expected. So, there is an observed frequency. So, with 0 value there are 10, 1 value 27, 2. So, we can say there are 10 students with a certain group of marks, 27 students with certain other group, 30 students with some other group of marks, 19 students with some other group, 8 students with some other group of marks, 6 students with, but we expect this. So, we want to look at the hypothesis whether they come from the same or not. So, what do? Observed minus expected square, that is this minus this square divided by expected, like that you keep on adding each one of these, okay. When you do that, okay, we get 1.45. Now, if you go to your table for 3, 4, 5, 6, okay. So, 5 degrees of freedom, we go to your table, okay, we go to our table for 5 degrees of freedom. So, if it is one sided, we take for 95% it is 11.07. So, we calculate as 1.45. So, we do not reject the null hypothesis. Do you understand this problem? So, here what we say is observed is equal to expected, that is our null hypothesis, observed is not equal to expected, okay, that is the alternate hypothesis. So, obviously the chi-square test statistics which we calculate should be greater than this value. Here we are taking for 5 degrees of freedom and for one side and 95%. Okay. Okay. Excel also has a function, it is called chi-test, that is actual range comma expected range, it gives you the statistics actually. Okay. So, let us look at this chi-test thing also in Excel. So, we go to Excel, so we say 10, we will put in the data 27, we put in the data 30, then we put it as 19, 8, 6, 13.5, 27, 27, 18, 9, 5.5. So, we do chi t, see you have this chi test comma so it is giving out actually it is giving you the probability, okay, 0.918. So, obviously the value is very very large, so there is no chance of rejecting the null hypothesis, okay, and that is what we get from our thing also here, okay. So, it gives you the from the statistics, okay, gives the statistics here, okay. So, it gives you 0.91. So, there is no chance of rejecting the null hypothesis from this data set. Okay. Okay, let us look at some more problems. Again looking, these are called contingency tables where we have expected and observed coming into picture. Okay, so we will look at some problems in this particular area. Okay, so results of a monohybrid cross between two heterozygotes for the A gene. Okay, so we are looking at it. The phenotypic ratio 85 of the A type and 15 of the small a type. Okay, this is the ratios. In a monohybrid cross between two heterozygotes, however, we would have predicted a 3:1. 3:1 is nothing but 75:25. Okay. Now, we want to know whether these results are very different. Okay. Okay. So, our null hypothesis will be, okay, there is no difference between these two observed and expected. Okay. So, if you remember this, they are same and their alternate is they are not the same. So, what do? We use the same formula, observed minus expected square divided by expected plus observed minus expected square divided by expected, add these two. So, we end up with 5.33. Okay. From the table, because it is 2 by 2, it will be 1 degree of freedom. So, we go to 1 degree of freedom, okay, it is 3.841. Okay. So, obviously the null hypothesis that two distributions are the same is rejected. So, we reject the null hypothesis, observed is equal to expected. Okay. So, once you reject the null hypothesis that the observed values of our cross are the same as the theoretical distribution of 3:1. So, generally we expect 3:1, but we find a phenotypic ratio of 85:15 which is not the same. Do you understand? So, we can again use the Excel also. Okay, so we can use the Excel also 85-15 and 75-25. 75-25. So, chi test actual divided by expected, we get 0.02. So, obviously p value is 0.02. So, obviously it is statistically significant. So, you see this from chi test we can also calculate chi test command which is available in Excel. We can, that is this one here, we can calculate these particular value. Okay, now there is a command called chi inverse. What is chi inverse? We give the probability, okay, we give the probability, say for example I give probability and 1 degree of freedom, say, okay. So, I need to get 3.84 as you can see here, okay. So, it gives you this chi inverse command is almost like your table, okay. So, chi inverse command 3.84, you understand, at 0.05 with the 1 degree of freedom, as you can see here 0.05 one sided comma 1 degree of freedom gives you 3.841. So, chi inverse is almost like your it gives you the table, whereas this one gives you the chi test gives you the probability. So, in the chi test we give the observed, okay, and then we give the expected on one side, we give the observed on the other side, okay, that way, sorry, yeah, expected on one side, observed on another side, okay. So, the actual and the expected that will give you the probability, whereas the chi inverse given the probability and the degrees of freedom, it gives you the chi square value as shown in the table, like 3.84 for example, 3.84. So, that is given in the chi inverse. So, both are very useful type of okay, and things to have when you are talking about, okay. So, chi distribution, okay, this is a older version for Excel 2007. So, we have chi test which if I give the observed and expected will give me the probability, whereas in the chi inverse when I give the probability and degrees of freedom, it will give you the chi square value. So, both these Excel commands are very useful also, but you can also do it by a simple calculator, because it is not very difficult for one to do. The formula is very simple: observed minus expected square, observed minus expected square it up divided by expected, okay, and then plus observed minus expected square divided by expected. So simple to do also, it is not very difficult for one to perform this type of calculations, okay. So, we will continue more of this chi square distribution again in the next class also. Thank you very much.